Welcome everyone to our journey through chemical processes and equilibrium. I'm excited to share this fascinating world with you. Today we are starting with the absolute fundamental, understanding how chemical processes work, from the moment reactants meet to the formation of entirely new products. So what exactly is a chemical process? Imagine you are a molecular architect. In a chemical process, you are not just rearranging furniture in a room. You are actually tearing down walls and building entirely new structures. When hydrogen gas meets chlorine gas, they don't just mix, they completely transform into hydrogen chloride, a totally different substance with completely different properties. The key here is that atoms are getting a complete makeover. They are breaking up their old partnerships and forming brand new ones, chemical bonds. Think of them as molecular handshakes are being broken and new ones are being formed. And here's the kicker. This always involves energy change. Some reactions give off heat. Others absorb it. It's like molecular drama. There is always energy involved when relationships change. Now let's clear up a common confusion. What's the difference between chemical and physical processes? Think of it this way. If chemical processes are like getting a complete makeover, new personality, new identity, then physical processes are just changing your clothes. When water freezes into ice, the molecules are still water, H2O. They are just moving around less, huddling together more closely. Same identity, different outfit. But when hydrogen reacts with chlorine, that's a complete transformation. It's like Clark Kent becoming Superman. Same atoms, completely different substance, with totally different superpowers. Physical processes are usually reversible. Melt the ice, you get water back. Chemical processes, where once Superman is out of the phone booth, it takes some real work to get Clark Kent back. Now let's learn to read the language of chemistry. A chemical equation is like a recipe, but instead of making cookies, we are making new molecules. Look at this equation. 2H2 plus O2, which will give us 2H2O. On the left we have our ingredients, the reactants. 2 hydrogen molecules and 1 oxygen molecule walk into a reaction. Sounds like the beginning of a chemistry joke, right? The arrow is our process. It's saying transforms into or yields. And on the right, we get our product, water molecules. Those numbers in front, they tell us the exact proportions. This isn't just add some hydrogen and oxygen. Chemistry is precise. We need exactly 2 hydrogen molecules for every 1 oxygen molecule to make 2 water molecules. No more, no less. Here where chemistry gets really elegant. Despite all molecular drama and transformations happening, the universe follows some absolutely fundamental rules. Conservation laws, these aren't suggestions. They are the non-negotiable laws of nature. First, the law of conservation of mass. What goes in must come out. Atoms don't just vanish into thin air or appear from nowhere. If you start with 4 hydrogen atoms and 2 oxygen atoms, you'll end with exactly 4 hydrogen atoms and 2 oxygen atoms. They'll just be arranged differently. Second, the law of conservation of energy. Energy can change forms, from chemical energy to heat to light, but the total amount never changes. Now let's meet the main character in our chemical drama, the different types of reactions. First up, synthesis reactions. These are the getting together reactions. Two separate entities meet, fall in love, and combine into something new. Magnesium meets oxygen and boom, magnesium oxide is born. Then we have the decomposition reaction, the breakup reaction. One compound decides it's had enough and splits into simpler parts. Hydrogen peroxide is unstable and breaks down into water and oxygen gas. It's the chemical equivalent of I need some space, except in this case the space needing results in bubbling and fizzing. Next up, we have the trading places reaction. Single displacement is like chemical musical chairs. Zinc comes along and kicks copper out of its comfortable spot with sulfate. Zinc sulfate forms, and copper is left standing alone. It's not personal, it's just chemistry. Some elements are more reactive than others. Double displacement is even more interesting. Silver nitrate and sodium chloride meet, and they decide to trade partners. Silver hooks up with chloride to form a precipitate, while sodium pairs with nitrate. Now for the showstoppers. Combustion reactions are the action heroes of chemistry. They are fast, dramatic, and always involve oxygen. When methane burns, it's not just combining with oxygen. It's releasing energy in a spectacular display of heat and light. This is the reaction powering your gas stove, your car engine, and keeping you warm by the fireplace. And finally, redox reactions. These are all about electron drama. Oxidation is when an atom loses electrons. Reduction is when an atom gains electrons. These reactions are happening constantly around us, in batteries, in our metabolism, even when iron rusts. It's all about electrons changing hands. So what makes some reactions happen easily while others need a push? Think of it like starting a conversation at a party. Internal factors are like personality. Some people are naturally outgoing, highly reactive elements, while others are shy, like the noble gas. The molecular structure and bond strength are like personal chemistry. Some combinations just click naturally. External factors are like the party environment. Turn up the music, which is increased temperatures in our case. Pack more people into the room, which is increased concentration. Or introduce a great host who knows everyone. Add a catalyst. Suddenly, conversations that seemed impossible are happening everywhere. The same principles apply to molecules. Change the conditions, change the reaction rate. Here is where things get really interesting. Breaking bonds costs energy. Think of it as paying to break up existing partnerships. But forming new bonds pays energy back. It's like getting a bonus for creating new relationships. The net result tells us whether our reaction is money maker or costs us energy. If we get more energy back from forming new bonds than we spent breaking old ones, we have an exothermic reaction. It gives off heat. If it costs more to break bonds than we get back, it's endothermic. It absorbs heat from the surroundings. Now, most reactions don't happen in one giant leap. They happen step by step, like a multi-chapter story. A reaction mechanism is like reading the director's cut of a movie. It shows you all behind-the-scenes action that leads to the final product. In chemistry, we have elementary steps. These are individual molecules events. Sometimes intermediate compounds form, like mixing the wet and dry ingredients before combining them. The slowest step determines how fast the whole process goes, just like the slowest cook determines when dinner is ready. Some chemical reactions are like one-way streets. Once you go down them, there is no turning back. When you burn paper, try asking for your original paper back. Not happening. These are irreversible reactions, and they usually involve a dramatic change, like combustion or the formation of a gas that escapes. But many reactions are more like revolving doors. They can go both ways. Nitrogen and hydrogen can combine to make ammonia, but ammonia can also break down back into nitrogen and hydrogen. These reversible reactions reach a balance point called equilibrium, like a perfectly balanced seesaw where both sides are equally happy. Now let's connect all this theory to your daily life, because chemistry is everywhere. Every time you cook, you are running a complex series of chemical reactions: browning meat, caramelizing onions, baking bread, all chemical processes that transform simple ingredients into delicious food. Your smartphone battery, that's electrochemical reactions converting chemical energy to electrical energy and back again. The photosynthesis happening in every green plant around you is converting carbon dioxide and water into glucose using light energy. It's nature's solar panel technology that's been perfected over millions of years. Even in medicine, drug development is all about understanding how molecules interact with biological systems. Every pill you take works because scientists understood the chemical process in your body well enough to design molecules that can modify them safely. So in the next lecture we are going to dive deeper into the energy story. So see you in the next lecture.